Welcome to Bayesian modeling. We'll start with understanding Bayes' theorem, the foundation of Bayesian statistics. Bayes' theorem is elegantly simple yet powerful. It states that the posterior is proportional to the likelihood times the prior. More formally, this can be written as P of theta given D equals P of D given theta times P of theta divided by P of D. Let's break down each component. The posterior represents our updated beliefs after observing new data. The likelihood is the probability of observing our data given specific parameter values. And the prior is our initial beliefs about the parameters before seeing any data. This diagram illustrates how Bayes' theorem combines prior knowledge with new data to form our posterior beliefs. We can visualize these components with simple icons. The prior is like a book containing our existing knowledge. The likelihood is like a histogram showing how our observed data is distributed. And the posterior is like a gauge that updates to show our new beliefs after combining prior knowledge with new evidence. Here's a real-world example of Bayesian updating in action. We start with a prior belief, observe new data, then form a posterior belief by combining our prior with the evidence. Let's see a practical application in medical diagnosis. If we start with a prior of 80% chance of disease based on symptoms, and our test is 85% accurate, Bayes' theorem gives us a posterior probability of 82% that the patient has the disease. To summarize, Bayes' theorem provides a powerful framework that allows us to combine existing knowledge with new evidence, quantify uncertainty in our beliefs, and update our understanding as more data becomes available. Choosing an appropriate prior is a crucial step in Bayesian modeling. Priors encode our initial beliefs before seeing data. They influence the posterior distribution, especially when data is limited and can affect computational complexity. Conjugate priors are prior distributions that, when combined with a specific likelihood, produce a posterior distribution in the same family as the prior. This mathematical convenience allows for analytical solutions, avoiding the need for complex numerical methods. Common conjugate pairs include the beta prior for a binomial likelihood, gamma prior for Poisson likelihood, and normal prior for normal likelihood. Let's look at an example of the beta-binomial conjugate pair. We start with a beta 1-1 uniform prior, representing no initial preference for any probability value. After observing 3 successes and 1 failure in our data, we update to a beta 4-2 posterior. The posterior remains in the beta family, demonstrating the conjugacy property. Non-informative priors express minimal initial knowledge or beliefs, allowing the data to dominate the posterior distribution. Common types include uniform priors, Jeffreys priors, which are invariant to transformation, reference priors, and maximum entropy priors. The choice between conjugate and non-informative priors depends on your specific situation. Use conjugate priors when you have strong prior knowledge, need mathematical convenience, or require fast computation. On the other hand, use non-informative priors when you have little prior knowledge, want the data to drive your conclusions, or need a more objective analysis. The choice of prior can significantly influence your posterior distribution, especially with limited data. Here we see how different priors lead to different posteriors, even with the same observed data. Both posteriors are based on the same data, 7 successes and 3 failures. Notice how the strong prior pulls the posterior toward its mean. A key point to remember is that with more data, the posteriors will eventually converge regardless of the prior choice. The core of Bayesian modeling is updating our beliefs as we observe new data. This is represented by the formula: posterior is proportional to the likelihood times the prior. This diagram illustrates how new evidence updates our beliefs through Bayesian inference. Let's visualize how our beliefs about a parameter theta are updated through Bayesian inference. We start with a prior distribution, representing our initial belief about the parameter. Here, we have a uniform prior, meaning we assign equal probability to all values. As we collect data, we calculate the likelihood function, which tells us how probable our observed data would be for different values of theta. The posterior distribution is formed by combining the prior with the likelihood. It represents our updated beliefs after observing the data. Notice how our belief has shifted and become more concentrated based on the evidence. The posterior peaks at the value most supported by the data. Here's a real example of how Alex's beliefs about a parameter theta were updated. The flat blue line represents the prior distribution, and the orange curve shows the posterior distribution after observing data. Notice how the posterior is more concentrated around 0.8, indicating that Alex has gained certainty after observing data. A key strength of Bayesian methods is the ability to perform iterative updating. The process starts with a prior distribution, representing our initial beliefs. We update this prior with our first batch of data to get a posterior distribution. This posterior then becomes our new prior for the next update. We can continue this process as new data becomes available, continually refining our beliefs. As we continue to update with more data, our posterior distributions often approach a normal distribution following the central limit theorem. With enough data, our posterior becomes increasingly precise, concentrating around the true parameter value. This demonstrates how Bayesian methods combine prior knowledge with evidence to refine our understanding. Markov chain Monte Carlo, or MCMC, is a powerful computational technique used in Bayesian statistics. When we can't solve for the posterior distribution analytically, MCMC allows us to explore complex distributions by generating representative samples. To understand MCMC, imagine a colony of ants exploring their environment. Ants naturally spend more time in areas with more food. Similarly, MCMC algorithms are designed to spend more time in regions of higher posterior probability, efficiently exploring the parameter space. Let's look at common MCMC algorithms. First, the Metropolis-Hastings algorithm. This algorithm works by proposing random moves in parameter space. It calculates an acceptance ratio based on the posterior probabilities and accepts or rejects the move accordingly. Gibbs sampling is another popular MCMC algorithm that updates one parameter at a time while keeping others fixed. In this illustration, we see how Gibbs sampling moves along coordinate axes, sampling from conditional distributions. The red dots show the path of the sampler through the posterior distribution. A critical aspect of MCMC is the burn-in period. Because the chain starts from an arbitrary position, initial samples may not represent the target distribution. These early samples are typically discarded. Only after the chain has had time to forget its starting point do we begin collecting samples. Convergence diagnostics help us determine if our MCMC chain has adequately explored the posterior distribution. We can check convergence through visual inspection of trace plots, statistical tests like the Gelman-Rubin diagnostic, or by analyzing autocorrelation and effective sample size. Once we have collected sufficient MCMC samples, we can summarize the posterior distribution in various ways. Typically, we compute point estimates, like the posterior mean, as well as interval estimates, such as the 95% credible interval. In this case study, we'll use Bayesian statistics to estimate disease prevalence in a population. Bayesian inference allows us to update our initial beliefs about disease prevalence with new evidence from testing data. For this problem, we'll use a beta-binomial model. The beta distribution represents our prior belief about disease prevalence. The binomial distribution models our test results, and the posterior is another beta distribution that incorporates both. The beta distribution is a flexible way to represent our prior beliefs about disease prevalence. It can take many shapes depending on the parameters we choose. The beta distribution is defined by this formula, where alpha and beta are shape parameters. For our study, we'll use a beta distribution with parameters 2 and 8, suggesting we believe the disease prevalence is around 20%, but with considerable uncertainty. To ground our discussion in reality, consider COVID-19 prevalence estimation, which was critical during the pandemic. Testing data helped update initial prevalence estimates. For our case study, imagine a community of 10,000 people. We test a random sample of 100 individuals and find that 30 people test positive for the disease. We start with our prior belief, represented by a beta distribution with parameters 2 and 8. This curve shows we believe the prevalence is likely around 20%. Our data shows 30 positive tests out of 100. The likelihood function is binomial, representing the probability of observing this data for different values of theta. When we update our prior with the new data, we get a posterior beta distribution with parameters 32 and 78. The posterior is simply the prior parameters plus the number of successes and failures. For a beta prior and binomial likelihood, the update rule is simple. Add the number of successes to alpha and the number of failures to beta. Our updated belief gives us a point estimate of about 29.1% prevalence, which is the mean of our posterior beta distribution. But a key advantage of Bayesian analysis is that it provides uncertainty quantification. Our 95% credible interval spans from 20 to 38%, representing the range of plausible values for the true prevalence. To summarize our Bayesian disease prevalence estimation, we started with a prior belief of about 20% prevalence. After observing 30 positive tests out of 100, we updated to a posterior belief of about 29%, with a 95% credible interval from 20 to 38%. Hierarchical Bayesian models extend traditional Bayesian approaches by organizing parameters in multiple levels, allowing information to flow between different groups. In a standard Bayesian model, we assume all data points come from the same distribution with shared parameters. In a hierarchical model, we organize parameters in multiple levels. This approach is represented using stacked plates notation, where nested rectangles indicate different grouping levels. At the top level, we have hyperparameters that govern the distribution of group-level parameters. The middle level contains group-specific parameters, which, in turn, influence the distribution of individual data points at the lowest level. A key advantage of hierarchical models is their ability to borrow strength across different groups. This means information from all groups contributes to each group's parameter estimates. As shown in this visualization, region-specific estimates in red are pulled toward the overall estimate in blue. The Bayesian hierarchical estimates in green represent a balance between local and global information. Groups with less data or higher uncertainty benefit more from this shared information. Hierarchical models are especially valuable when some groups have limited data. In these cases, the model can supplement the sparse information with knowledge from other more data-rich groups. These histograms demonstrate how a hierarchical model distributes parameters across different groups. Each panel shows the distribution of parameters for different groups and their differences, allowing us to quantify the shared information. Let's consider a practical example of a healthcare system with multiple clinics. When assessing treatment effectiveness, smaller clinics with fewer patients benefit from information shared across the system. In a hierarchical model, information flows between clinics. The small clinic's limited data is supplemented with relevant information from larger clinics, resulting in more realistic and stable estimates. To summarize, hierarchical Bayesian models organize parameters in multiple levels using stacked plates notation. They allow information sharing or borrowing strength across groups, which is particularly valuable when some groups have sparse data. These models strike an optimal balance between pooling all data together and analyzing each group completely separately. Bayesian modeling offers several key advantages over traditional statistical approaches. The first major advantage of Bayesian modeling is the formal incorporation of prior knowledge. Unlike frequentist methods, Bayesian approaches allow us to encode expert knowledge as mathematical priors, combining existing information with new data. This is particularly valuable when datasets are small, but prior information is strong. The second advantage is full uncertainty quantification through posterior distributions. Bayesian methods provide complete probability distributions rather than just point estimates. This quantifies our confidence in different parameter values and enables more nuanced risk assessment in decision-making. The third advantage is the ability to make probabilistic predictions within a coherent framework. Bayesian methods provide predictions with full probability distributions. This coherent framework combines multiple sources of information, leading to more informed decision-making under uncertainty. The fourth advantage is the ability to make adaptive decisions as new data arrives. We start with a prior belief about our parameter based on existing knowledge. As new data arrives, we calculate how likely that data would be for different parameter values. Then we update our belief to incorporate this new evidence, creating a posterior distribution. This process happens systematically as new data arrives. Yesterday's posterior becomes today's prior, creating a natural framework for sequential decision-making. To summarize, Bayesian modeling offers 4 key advantages: formal incorporation of prior knowledge, full uncertainty quantification, probabilistic predictions, and adaptive decision-making. Together, these advantages provide a powerful framework for decision-making under uncertainty across numerous fields. In Bayesian modeling, validating your models properly is crucial for ensuring robust and credible results. We'll focus on 2 essential validation practices: prior sensitivity analysis and posterior predictive checks. Prior sensitivity analysis examines how your choice of prior distributions affects the posterior inference. This is essential for understanding the robustness of your model. Here we see how a flat prior distribution in blue leads to a concentrated posterior distribution in orange. The black vertical lines represent the 95% credible interval. To perform proper sensitivity analysis, use different prior distributions and compare the resulting posteriors. This helps identify how sensitive your conclusions are to your prior choices, allowing you to report results with appropriate uncertainty. Posterior predictive checks are a powerful model validation technique that compares simulated data from your model with the actual observed data. In this visualization, the thick red curve represents our actual observed data, while the thin pink curves show simulated data from our posterior distribution. If our model is valid, the simulated data should resemble the observed data. The posterior predictive distribution involves integrating over all possible parameter values, weighted by their posterior probabilities. This formula shows how we generate simulated data based on our posterior distribution of parameters. Beyond sensitivity analysis and predictive checks, understanding your model's underlying assumptions is crucial for proper validation. This figure illustrates a comprehensive approach to model validation, showing posterior distributions for key parameters, regression diagnostics, and uncertainty intervals. These visualizations help assess whether your model assumptions align with your data. To ensure robust Bayesian modeling, validate with multiple approaches, check sensitivity to prior choices, compare model predictions to real data, carefully examine your model assumptions, and thoroughly document your validation process. Bayesian modeling is supported by a variety of specialized software tools that make implementation accessible to practitioners. STAN is a state-of-the-art platform for statistical modeling, providing full Bayesian inference with Hamiltonian Monte Carlo. JAGS, or Just Another Gibbs Sampler, specializes in Bayesian hierarchical models using Markov chain Monte Carlo simulation. PyMC3 and PyMC4 are Python libraries that simplify the process of building and sampling from Bayesian models. Both R and Python offer extensive packages for statistical computing, data analysis, and visualization with Bayesian capabilities. Let's examine how JAGS visualizes Bayesian model outputs to help assess model convergence and parameter distributions. The trace plots on the left show how parameter values change during MCMC iterations, helping us assess convergence. The density plots on the right visualize the posterior distributions of model parameters. JAGS is particularly useful for regression analysis with Bayesian methods. These diagnostics show parameter estimation, autocorrelation, and convergence metrics for a regression model. As we conclude our exploration of Bayesian modeling, let's examine its power and the technological advances, making it more accessible. Bayesian analysis elegantly combines prior knowledge with new data to form posterior distributions that represent our updated understanding. Today's Bayesian methods are increasingly integrated with machine learning, offering transparent uncertainty quantification and improved decision-making frameworks. Bayesian modeling turns data and expertise into coherent probability statements, empowering informed decisions under uncertainty.